So I think the idea of this is to it's quite informal, right? So this is just a talk that I gave a few weeks ago, so I'm going to rehash that, but I think the idea is to sort of interrupt at will and try to, sort of engineer discussion. So I'm going to tell you about work that I've been doing for a few years now, predominantly with the manual caliper on the cosmological constant problem. So what this picture is supposed to show is, of course, is Atlas, and he looks like he's holding up the world. What the sort of message I'm trying to get across here is that, in a sense, when you think about the cosmological constant problem, what you're really doing is you're sort of holding up the whole universe. You're kind of weighing the entire universe when you talk about the value of the cosmological constant. And one of the things that I want to emphasize is that within effective field theory, the cosmological constant is not something that we should expect to predict the value of. It's something that we should just go out and measure, okay? Because it's a relevant operator, and you don't really expect to predict the values of relevant operators in effective field theory. What you do want, however, is that this guy should be radiatively stable. So, for example, something like the mass of the electron is again something that within effective field theory you don't expect to predict, so you just measure it, but it's a radiatively stable quantity. It's robust against radiative corrections. That's not the case with the standard story of the cosmological constant, as I'll explain. So what Nemanja and I tried to develop was a sort of a theory which tries to make the cosmological constant something that's radiatively stable, but we don't actually predict a value for it. Okay, it's something that we say you go out and measure. So in that sense, we're promoting it within the level of effective field theory to something like the mass of the electron. So everybody always has their own version of what the cosmological constant problem is. I'll explain what I think it is and what we're trying to address here. And the general approach that we're going to have is that we're going to look at the cosmological constant. We're going to identify it as something that's kind of unique in terms of all the sources of energy and momentum that you have in gravity. And the thing that's unique about the cosmological constant is sort of what it says on the tin. It's constant, okay? It's genuinely a constant. It doesn't change, it's constant everywhere in space and time. So if you want to try to tackle the cosmological constant problem, and you want to do that perhaps by modifying gravity, the minimal thing to do is to modify gravity literally at that level, just at infinite wavelength at the constant level. And that's what the sequestering proposal, at least as a first pass, aims to do. So I want to just show you this sort of flowchart that I was in a meeting in Denmark last year, and McCullen put this up on the wall. It was a meeting about naturalness, and so have you solved the cosmological constant problem? And you're supposed to take your model and you're supposed to follow this flowchart through, and of course all roads lead to no. So I think this says a little bit, basically less anthropics, by the way. I think this suggests that perhaps McCullen is a little bit biased towards anthropics. Do you vote anthropics? No, therefore you're wrong. No. So the question is, where does sequestering appear on this little drawing? And the answer is, it's not killed by this drawing, because sequestering is weakly anthropic in the following sense. It's the sense that I've just said, actually. We don't predict a value for the cosmological constant. We don't demand a small cosmological constant. We go out and measure that. The question is it radiatively stable? Okay, so in that sense, it's weakly anthropic. Okay. So let's just let me do credit to my collaborators. Here's a bunch of papers that we've written on this now. There's more in the pipeline with people here. And I'm actually going to touch as well towards the end on some recent work that I've done with Florian, which is we find quite interesting, quite exciting, and it's a nice way of understanding sequestering within the context of Weinberg's no-go theorem, and really understanding how, perhaps a little bit more deeply, about how sequestering is working as a theory. So let me just begin by discussing what the cosmological constant problem is. I don't want to spend too long on this because I think everybody has a rough idea, but I want to sort of pin down some important points. So you know that in quantum field theory you have a vacuum energy, and you know in general relativity to use the equivalence principle, that all forms of energy gravitate. And you know how they gravitate, because general covariance tells you how they gravitate. So in particular, the vacuum energy will gravitate like a cosmological constant. Okay, but of course it's not that vacuum energy, which in principle, you would regulate it, remove the divergences and so on and so forth. You can always add to that a bare cosmological constant. Of course, it's the combination of the bare guy and the vacuum energy that gravitates. And that combination shouldn't exceed the dark energy scale. That's the observational test of it, okay? So then you go away and you say, well, how big is the vacuum energy? And you can do this in a fancy way. You can do it just by summing up all the harmonic oscillators of all the particles you have in your theory. Either way, what you find is that each particle contributes its mass to the fourth power, to the vacuum energy, right? And you get contributions all the way to the cutoff of your theory. But the point is, these contributions go like fourth power of the mass, which means they're dominated by the UV part of the theory. The heaviest particles in the theory are dominating this. Okay. So this is clearly sensitive to the UV sector of your theory. So then you start to freak out, because you start to realize that even if you just cut off your theory just above the scale of the electron, right, it's a pretty low scale as far as particle physics is concerned, big MeV to the fourth, then you already have to fine-tune your bare value of the cosmological constant to 36 decimal places to get down to the observed value. And of course the situation just gets worse and worse and worse as you move up the scale. So this should be compared to really understand what the issue is. We should compare and contrast this with the situation with the electron mass. Okay, so you can ask, what are the quantum corrections to the electron mass in some effective field theory? And what you find is that they go logarithmically, like the cutoff. So they're still sensitive to the UV part of the theory, the unknown UV part of the theory, but only logarithmically. Okay. The important point is these corrections will go to zero as the electron mass itself goes to zero, and that happens because you have an extra symmetry in the limit where the mass goes to zero, which is chiral symmetry, and that's what protects the mass from uncomfortably large corrections. That's what you mean by radiative stability. Indeed, because it's a coupling of a relevant operator in your theory, it is UV sensitive. However, it's only very mildly UV sensitive. And actually, you can understand the enhanced symmetry in the limit where the mass of the electron goes to zero. And that's what you mean by radiative stability. And that is in stark contrast to the situation with the vacuum energy. So vacuum energy, you have a situation where the corrections are growing like fourth powers of the masses. That's extreme sensitivity to the UV part of the theory. In contrast, the electron mass is only very mildly sensitive to the UV. And that's really what you mean by the difference between natural and unnatural within an effective field theory context. It's not really the question of why something's small in this context. It's really how sensitive you are to the unknown physics. If I tweak the mass of some heavy particle by, say, a factor of 2, okay, that's barely going to do anything to the prediction for the electron mass at low energies. But it will drastically change your prediction for what the cosmological constant should be, so you have to retune. Okay, and this is really the problem with naturalness. So what you want to do with the cosmological constant is you really want to promote it to something like the electron mass. You want to put it at that level. Okay. Now, if you want to work on some UV complete theory and actually predict what the CC is, that's fine, okay? But that's not really what the question of naturalness is at the level of effective field theory, which is really the only well-defined problem in the context of the cosmological constant. And the other important point to realize is that these aren't things that you predict in effective field theory. They are things that you measure. You do not predict the electron mass in effective field theory, okay? You measure it. And nor should you predict the cosmological constant in effective field theory. You measure it, but you do want it to be radiatively stable. So how do you do that? Okay, well, it's tricky. Okay, that's the problem. Particle physics, you could use supersymmetry, but of course, unfortunately, the scales are all wrong, right? Supersymmetry broken scale has got to be at least at a TeV scale, but we really want to get this down to a milli-electron volt scale. So the scales are all wrong, so you can't use SUSY. Okay, so maybe you could look to modifying gravity. And here the philosophy would be, and this dates back to the 1980s really, the philosophy would be that these large radiative corrections are there, correcting the cosmological constant, but for some reason they don't gravitate. So perhaps there's some additional fields that adjust themselves, self-adjusting fields they sometimes get called. These additional fields adjust themselves and they protect the metric from that large correction to the cosmological constant. Now the trouble is, the minute you do that, Stephen Weinberg comes and punches you in the face, okay? And he has this wonderful no-go theorem from the 80s, which basically essentially tries to rule out this possibility. But of course, like any no-go theorem, it depends on certain assumptions, very valid assumptions, very reasonable assumptions, but it is only as good as its assumptions. Okay, and actually, towards the end of the talk, I want to talk about work that Florian and I have been doing, where we've tried to take Weinberg's theorem off in an orthogonal direction. So relax some of his assumptions and come up with a new sort of complementary no-go theorem, if you like. But also has loopholes which are interesting. Okay, so I now want to tell you the story of sequestering, okay, and I'm going to tell it sort of chronologically. So I'm going to start with the original manifestation of the model. The model is more sophisticated than this now, but I think it's important to do this because it allows you to see really how it's working. Okay, we will talk about the local versions later on. Okay, but I want to start with the global version of vacuum energy sequestering. So here's the starting action, which of course you will recognize as just the action for general relativity, with matter minimally coupled to the metric, and you've got some bare cosmological constants. This of course is horribly radiatively unstable. Okay, the vacuum, this suffers from the cosmological constant problem clearly, right? So what do we do? So we realized there were two sectors that we were interested in sort of balancing off against one another. On the one hand, you've got the bare cosmological constant here, and on the other hand, you've got the matter sector. Okay. So we said, right, well, we'll promote the bare cosmology. We want to introduce some global dynamics. Okay, we're going to do this minimal thing of modifying gravity, but only globally. So we're going to promote the bare cosmological constant to a global dynamical variable. So this is something like a Lagrange multiplier. You vary over it in the action, but it's not space-time dependent. Okay. And we're also want to know something about the mass scales in the matter sector. So we're going to rescale the metric in the matter sector by another one of these global dynamical variables. So a constant, but something that we're going to vary over in the action. So this guy's the bare cosmological constant, and this sort of is like a rescaling of all the mass scales in the matter sector. So we've got these two variables, we're going to vary with respect to them, and then we also want them to talk to one another, so we introduce an interaction term. Now, this interaction term is a global interaction, so it sits outside of the integral, which, before you start vomiting at that thought, bear with me, we're going to be getting local later on, but for now, just accept it. Okay? So, what is the dynamics that you get from this setup? Okay, so it's a global modification of gravity, but what does it actually give you? So you just derive the equations of motion. Of course, you get Einstein's equation coming from the metric variation, but you also get two global equations because you've got these global variables. And they do something very interesting because they tell you exactly what this counter term should be. Okay, you can just take the ratio of these two equations and you realize that the bare cosmological constant should be given by the space-time average of the trace and the energy momentum tensor. Okay, space-time average, that's important. So you see what happens. You feed that back into the Einstein equation. Something very kind of cute happens. You end up with this effective gravity equation. So this is essentially the equation of motion you would get once you've integrated out those global degrees of freedom. But look at the structure of it. Now you can ask yourself, what happens when I plug in vacuum energy to this equation? So you split your energy momentum tensor up. So So you split it up essentially into the infinite wavelength part, which is the vacuum energy, plus local corrections. Okay. Now, the cute thing about this part, well, it has two cute things about it. One, it's a constant, and the space-time average of a constant is the same constant. And two, it's a pure trace. So actually, when you feed it back into this equation, this guy just drops out completely. Okay, it just drops out and you're left with just the local pieces. So what's happened is all the nasty radiative corrections to the vacuum energy, which all live in here, are gone from your effective gravity equation. And you'll end up with just a theory that was built out of these local excitations. Now, that's not to say that there's no cosmological constant. There is. This guy is a cosmological constant. It's a space-time average of stuff, so it's a constant. Gravitates like a cosmological constant. But it's got nothing to do with those troublesome radiative corrections. It's completely independent of them. They're gone. Now, this happens no matter how you calculate your vacuum energy. You can calculate it to 1 loop, 10 loops, 20 loops, it doesn't matter. You can calculate it with this cutoff, this cutoff, this cutoff, it doesn't matter. It will drop out. Okay? This might seem reminiscent of unimodular gravity for those people that know what that is, where essentially unimodular gravity is just GR, actually. It's just GR where you assume that you do the variation of the Einstein-Hilbert action assuming the determinant of the metric is fixed to be 1. And then you end up with the traceless Einstein's equations out. But then you hit that equation with the derivative, use the Bianchi identity, and you end up with Einstein's equation again. Okay? So there's hidden equations in there. Here there are no hidden equations. This is it. Okay? It's completely covariant.
I have a very naive question.
Yes?
Question is, as you explained, the cosmological constant problem is a quantum problem in the sense that it's quantum fluctuations that gravitate. This is a classical solution for it, right? This is a modified yes, I think this is appropriate because the most well posed version of the cosmological constant problem is within quantum matter coupled to classical gravity. Then there is definitely a well posed cosmological constant problem. And so this is essentially a classical gravity theory coupled to quantum matter. We can also think about quantizing the gravity sector. So the minimal thing to do would be, of course, to do like perhaps John Donohue's type approach, treat gravity as an effective field theory as well. So the first model I'm going to propose would have problems with loops of gravitons coming from those, but actually we have a sort of more sophisticated version which doesn't, which can even cope with those contributions. So this is really QFT in classical, right?
Yes, exactly. Now, if you want to start talking about a full quantum theory of gravity, i.e. string theory or whatever, then, well, now you're not really talking so much about effective field theories now, so no, it's not really the same problem.
But you can talk about gravity and matter as effective field theory.
Yes, absolutely. So the simplest version of the model will have a problem with the graviton loops, but there is a generalization which doesn't. Okay.
Do you think you have dim reg here?
It actually doesn't matter. It doesn't make any difference. Yeah, you could do dim reg if you wanted, but actually it's completely independent of the regularization scheme, as you'd want it to be, really. Okay, so is there symmetry at work? Okay, there is. Whenever you get a cancellation like this, of course there's symmetry at work. There's a scaling symmetry and a shift symmetry. Well, I mean, the details, I don't want to dwell on that, but there is a symmetry there, okay? Okay, about the symmetry.
That once you modify gravity, it has extra symmetry now?
This has an extra symmetry, does have an extra symmetry, yes. Okay, so, well, I mean, well, it is what it says on the tin, right? So there are two mass scales I had there, right? One was the Planck mass, one was this mass scale mu, which was introduced for dimensional reasons, and you can think of it as up being near the cutoff of your theory. If you take those two scales to infinity, there's exact symmetries that emerge. One is, again, the scaling symmetry, one is a shift symmetry. Actually, in the improved version that I was telling you about to deal with so actually the fact that it's actually the shift symmetry gets broken by M. Planck is the reason you have problems with graviton loops. So in the improved version, we have the shift symmetry remains intact.
It's a shift symmetry. What do you shift?
One of the global variables. Now you might worry about UV completing a shift, global symmetries and embedding them in quantum gravity, which I think is a legitimate thing to do. But you probably try to embed this in something that could cope with that.
So are you saying that this explanation, or the reason why the model works, is the same as for the electron mass? There is approximate symmetry.
Yes, there is an approximate symmetry. This is the approximate symmetry.
Okay. Any simple physical system where there is a global variable, and how can I understand this global variable? Why should I vary the action with respect to them? Right? I usually vary the action because of define the action as an integral over space-time.
I mean, there's loads of physical systems where you hold a global variable fixed. Any of these sorts of, I'm trying to think of these. I mean, anything that has a global constraint in the system. So you impose some sort of global constraint on the object you're looking at. That will have global. You have to introduce a global Lagrange multiplier that will constrain that. So any mathematical problem like that would have such a thing.
You have physical sort of interpretation of what these global variables are.
So the way you should think of it is that basically you're adding global constraints to general relativity. And that's, you add one global constraint to GR, and that's enough to take care of this issue. Now you're already, by introducing the cosmological constant, you're introducing something global to the theory. So it's not such a radical step to make that leap.
Yes. Instead of saying it's a constant and saying it's a global variable and I have to vary with it.
Well, or say I'm adding a global constraint to my theory. Yeah, then.
Similar question. So if you promote this to a local,
which I'm going to do.
Okay. Well, very good.
Okay, but first let me just talk about. So there's been a few papers recently, and not so recently, which attempt to modify gravity globally and actually apply that to the CC problem. There's a few. I'm going to talk about a couple of them. Just because it's quite illustrative in trying to understand. So none of those models quite work. It's quite interesting to try and understand why they don't work and how they might be fixed. And it is going to lead us towards sequestering, actually, so it's a bit biased. But let's have a look. So this is work that we did recently with Nemanja and other collaborators, Westphal, Guido D'Amico, and David Stefanishin and George Zahariada. Okay, so first I want to go back to actually what was the real inspiration for sequestering way back when, which is this model by Saitlin, which is inspired by string theory. And what Saitlin did was something very, very simple, very, very clever. He just took the action for GR and divided it by the space-time volume and called that his new action. Okay? Now that seems like a very clever thing to do. It is a very clever thing to do. And the reason it's quite cute is because you know how the cosmological constant is going to enter here. It enters as a constant times the volume, the space-time volume. And then you're dividing by the space-time volume, so you're dividing out the metric dependence completely from that term. And so the cosmological constant looks like it's not entering the game. It's kind of cute. Right, very good. Well, does that work? And the problem is it doesn't.
It's also non-local.
It is non-local, but that's fine. Let's suppose what I had. You can easily make it local in the same way that I'm going to make ours local, but that's not really the question I want to dwell on here. What I want to ask is, does it even solve the cosmological constant problem? And it doesn't. And the reason it doesn't is you can see quite easily. So in quantum field theory, you normally think of it's not always true, but generally true, that the powers of h-bar count the loops. Okay? So powers of h-bar count the loops. Now by dividing through by the space-time volume, what Saitlin's really done is he's introduced an effective h-bar, which goes like the volume of the space-time. Okay? So when you do the quantum corrections, generically what you'll find is that you'll get extra powers of h-bar effective, which now knows about the space-time volume. So it's only the tree level piece that is divided by the space-time volume. All the quantum corrections scale differently. And so the nice cancellation that you got at tree level completely fails at the quantum level. Okay? And so you haven't addressed the problem of radiativity at all. Okay, so it just fails. Now you can fix this.
So this is what Nemanja and I, this was really the first step in developing sequestering, was to try and fix this. So what you want to do is you want to make sure that all the quantum corrections are scaling with that space-time volume in the right way, in the same way. And you can do that by exploiting the universality of the matter coupling. All you have to do is say that matter couples to some rescaled metric that knows about the space-time volume. Okay? And then it turns out that all the quantum corrections will all scale with the same power. The vacuum energy corrections will all scale with the correct power of the space-time volume. And this is the first ever sequestering theory. That sounds like really sort of historical. It's not historical. This is the first ever sequestering theory, and all the others are sort of generalizations of that. So Sean Carroll and Grant Remen also, this is much more recently, this is this year, also wrote down a theory that was supposed to be a global modification that addresses the cosmological constant problem. So what did they do? Well, lots of very similar ingredients to sequestering. So on the one hand, they had this four-form kinetic term. Okay, a four-form kinetic term gravitates like a cosmological constant. Okay, so the idea is that this guy is going to act like the cosmological counter term, the bare cosmological constant that cancels off the vacuum energy. They also had this global variable here, eta, which multiplies the whole action and will give you a constraint that forces the whole action to vanish. And they mumbled something about how this comes from the joule of some four-form that's been integrated out, blah, blah, blah. Okay. Okay, fine. Does this solve the CC? Okay, that's the wrong way. Okay, so
Sorry, again, my question. Is this a valid effective field theory? How do you quantize it?
We'll come back to let's not. I don't want to. I'm going to. Let's talk about that in the context of sequestering, not in this theory, because this theory doesn't work either. Okay, but I want to understand why it doesn't work. Okay, so you have this global constraint coming from eta. The idea is it forces the action to vanish, and that forces, according to these guys, this counter term, this gives you a bare cosmological constant to cancel the radiative corrections from the vacuum energy. That's the claim. Except it doesn't quite work. Why not? Okay. All right. So first step. Okay, you need your bare cosmological constant to adjust. Okay, it needs to be able to cope with any vacuum energy and cancel it. Okay, so if it's an integration constant that's fixed by a boundary condition, which here it looks like it's going to emerge as an integration constant when you use the four-form equations of motion. But if that's then fixed by a boundary condition, it's fixed. It's just a constant. Nothing you can do with it. Okay, you say, all right, fine. I'm not going to make that the case. If this four-form is coupled to membranes as you'd expect it to be in string theory, it will be quantized. That's also a problem because you want to be able to continuously adjust, to be able to cancel any vacuum energy. So that's a problem. But you say, okay, I'll give them the benefit of the doubt. I'm not going to assume that I'm going to assume that it's not quantized, that it's not an integration constant. So can I still solve the cosmological constant problem? And the answer is no, still no. Okay, and the reason not is this global constraint coming from eta, this variation with respect to eta. Well, eta now enters an effective H bar. Okay, so when you calculate the quantum corrections, you're going to get extra powers of eta appearing, and you're going to change the global constraint. And the solutions to the cosmological, this only cancels the vacuum energy at tree level. It doesn't deal with the loops for exactly the same reason as Saitlin had a problem. So then you say, how can I fix it? Well, you can fix it. You can fix it very simply by just moving this global parameter here. Okay, now it's not an effective H bar, it's actually an effective Planck mass. It's now changing the Planck mass. And you get a different global constraint. The global constraint you now get is that the space-time average of the Ricci scalar should vanish. Okay, so it places a global constraint on the geometry rather than the geometry plus the radiatively unstable matter sector. This simple modification of the theory is actually sequestering, again, written in a slightly different way to what we normally write it.
It's a hybrid of what I'm going to call the local and the global version of sequestering that I've just discussed. Okay, so it does seem as if all these roads lead to sequestering, but now, so I want to go back to my sequestering theory, and we're going to try to make the step now into a local theory. Okay, but the first step I want to do that, I want to acknowledge that I can think of this in two different frames. So as I wrote it the first time, you can think of this as like Einstein frame. I've got a standard Einstein-Hilbert term, and I've got all the global stuff sitting in the matter sector as well as the cosmological constant. I can switch frames, okay? So I just redefine my metric, so absorb this lambda into this metric, redefine some of the global variables, and I get like a Jordan frame action, for those people who know this jargon, in which matter is just minimally coupled to the metric. I still have a cosmological constant counter term, a bare cosmological constant, which I'm going to vary over. But now I also vary over the Planck mass, because this little lambda dependence has gone into the Planck mass. So I should also vary over the Planck mass. And this is kind of a nice way of thinking about sequestering, because what you have now is, you think about what I've actually done here. I've promoted the two relevant couplings of gravity, i.e. lambda and the Planck mass, and made them global variables. It's almost like, is that something you're supposed to do? Okay, so yeah, I've redefined lambda as well. I've redefined lambda as well, because when you redefine when you absorb little lambda into G, you then pick up little lambda dependence from the root G, which multiplies this guy, so you absorb that into a new definition of that, and in the end you end up with that. Actually, it's remarkable. I think it's probably telling you something about how to embed this in a deeper theory.
So kappa just gives you global constraint.
Yes.
What's your average?
Exactly. So look, exactly. This is what kappa is doing. Very respect to kappa, and you get a constraint on the geometry, a global constraint on the geometry. Okay. And then the idea is that lambda would adjust accordingly.
Just
to satisfy that.
Switch off matter and consider homogeneous isotropic universe. What solution can you get in this theory?
So in no matter.
No matter.
Well, of course, you can have maximally symmetric solutions in this theory.
Which one will you get? Will you get lambda equal to 0 solution?
If you have no matter, yes. Because the effective gravity equation is g mu nu equals t mu nu, and then the effective cosmological constant knows about the matter content, and it's space-time average of the matter content. You're saying that's not there, so yeah, indeed, you just have g mu nu equals 0. So yeah.
It's just a similar point. So it's not just no matter, but also if your matter Lagrangian here is scale invariant, then you can absorb the lambda into field redefinitions for all of your matter fields, which means that the standard part of the action there doesn't depend on lambda for a scale invariant.
Well, yeah, but this clearly you can't breaks it, right?
No, I mean, so the lambda's the four matter Lagrangian piece doesn't depend on lambda for a
but also if your matter sector is scale invariant, then there's no cosmological constant problem.
That's not true if you have spontaneous scale invariant.
Okay, so but then the Vev association with that is the guy that breaks the scale invariance, right? So that's exactly the thing that's given all the masses, which is the thing that's important.
Great, and what's the explanation for small lambda?
I'm sorry, no, that's a measurement. That's a measurement. You would have to build this theory into the UV to try to understand why it might be small.
But even this theory cancels lambda completely. Lambda is 0. So where can lambda...
That doesn't mean the cosmological constant is 0. So it cancels the radiative corrections, but there is that leftover piece in the effective gravity equation, which is the space-time average of the trace of the local sources. So that's not it's not 0. Look outside and it's not 0. So that you can't, that in principle you should just measure. So it doesn't, yeah, anyway.
What do you mean by varying quantum theory? Do you mean there's
okay.
mechanical variables and you should integrate over them?
Yeah, I mean, if you want to, you can try to Okay, maybe it's better if I go to the local theory, and then that'll be less controversial. Okay, if you wanted to think about how to, even if I don't do that, okay, let me say this: you might worry about where you get these guys from, these things that sit outside the action. We're worried about it. Now, you can get corrections like this when you integrate out wormholes. When you go back to Coleman's wormhole games in the 80s using Euclidean quantum gravity, you integrate out wormhole corrections and you integrate out the smallest wormholes and below some scale, and then you end up with corrections like this to the action actually that are global. It kind of makes sense if you're integrating out wormholes. And there, what you end up with is an effective path integral where you have a variation over but it's not a functional variation, it's just like an ordinary variation because it's a global variable of the global parameters. So you'd end up with an ordinary variation over lambda, not a functional one. Yes, an ordinary integral, yes, sorry, yeah, integral. Okay, but we're going to go local anyway, so because it's, okay, so why do you need to go local? Well, you want to ultimately think about embedding this in some fundamental theory. Okay, so you better be consistent with quantum mechanics. Okay, now quantum mechanics demands an additive action, linear superposition, and the way you build the path integral formulation of quantum mechanics, it uses the fact that the action from A to C is the action from A to B plus the action from B to C. That global piece, that sigma term in our action breaks that. So it's bad from that point of view. Now you can mumble on about wormholes if you want, but the whole wormhole game it's not clear that it was particularly well understood, it's not clear if it's robust, and there were problems with it anyway. So it's, we'd like to do something else. We want to make it local. We want to come up with a local action. So to do this, we came up with a lesson from unimodular gravity. So in unimodular gravity, as I mentioned earlier, you just take GR and you assume the determinant of the metric is 1. Okay, so you can implement that using a Lagrange multiplier, like so, straightforward. Now, this 1 here has two interesting properties. It doesn't gravitate, okay, 1 has no metric dependence, so it doesn't gravitate, but it also breaks diffs, okay? So what Henno and Teitelbaum did, they wanted to replace it with something that they wanted a diff invariant theory. So they wanted to replace it with something that retained diffs but still didn't gravitate, to retain what they thought were the nice properties of unimodular gravity. So you can do that just by trading this 1 essentially for a 4 form. More correctly, a joule of a 4 form. And this has no metric dependence. So you can think of this 4 form as being the derivative of the 3 form. It has no metric dependence, so this will not enter Einstein's equation. Okay. It also has the nice property that when you vary the 3 form living in there, it will force this Lagrange multiplier to be constant. That's kind of pushing us to a global limit. Okay. And we retain diffs. So it smells of the kind of thing that we would like to introduce in our theory. So can we use it? So as a first step, we take our action more in the Jordan frame, and we just, those things that were previously global parameters, okay, we're now just going to generally make them local fields. So the Planck mass is now going to become a field, and the bare cosmological constant is going to become a field. So this looks a bit like, that would look a bit like, Brand's-Dickey gravity, for example. However, we want to force ourselves into this global limit without introducing any more local dynamics. So we use Henno and Teitelbaum's trick. Okay, we add 4 forms, which are derivatives of potentials associated with 3 forms. So now what this guy's got, neither of these two terms gravitates. Okay, there's no metric in here. All right. The variation of the 3 form living in here forces the constancy of lambda. The variation of the 3 form living in here, which is a different one, forces the constancy of the Planck mass. But you still retain their global part, their global variations. You don't kill that. And this is essentially the local form of sequestering. So what are the field equations you get from it? So you get the generalization of Einstein's equation from the metric variation, which looks a little bit like Brand's-Dicke gravity, but not exactly. You get something which comes from the variation of the scalars, i.e. lambda and kappa. You get two terms coming from there. And you also get the three-form variations that force the constancy of the parameters lambda and kappa that we've now made local. Okay. So you can integrate out, you can play the same game and you integrate out everything but the metric. What are you left with? You end up with an equation that's very similar to what we had before. Okay, this is now a constant, right, in space-time. You end up with this same structure that we had earlier, plus a correction. We'll look at what that is. So this guy we already have argued is radiatively stable from the vacuum energy corrections. Doesn't care about them. What about this? Well, it turns out that this guy, this correction, which is like a cosmological constant correction, it essentially knows about the fluxes of the three forms through the boundary. The flux of these four form fluxes through the boundary. Okay. So is that radiatively stable? And it turns out it is. So let's see why. So you can ask how vacuum energy corrections change some of the parameters of our theory. Well, it's going to shift this lambda variable by fourth power of the cutoff, and it'll shift the kappa variable by the square of the cutoff. Now, as long as you take all your scales up at the cutoff or above, then, and these sigma functions are nice and smooth, nothing too sharp living in there, then these sigma functions are going to vary by order 1 at most. Those fluxes, well, they're exact four forms. So these really are fluxes of three forms through the boundary. They're geometric infrared quantities. They've got nothing to do with the UV part of the theory. So what you now have is, what this tells you is that under a radiative correction, this extra piece just changes by order 1 times itself. Okay, that's what you mean by natural. Okay, that you don't get a large change, you get back the same thing essentially. How does this work? Why is this happening? Well, a nice place to look at the dynamics of this is to zoom in, well, where it's really happening actually. So it's happening in the trace part of the theory, and on the space-time average in the global part. So what you can do is you can take the trace of your equations and the space-time average, and that zooms in on the interesting dynamics actually. So if you do that, you end up with these equations. Now it just so happens that this last equation here is also true in general relativity. If you take Einstein's equations, take the trace, and take the space-time average, this is what you'll get. Okay? The difference is, as a question, you have these extra global terms as well. So let's compare what happens in general relativity to what happens in sequestering. So in GR, what you do is you fix the counter term, the bare cosmological constant. Now there are radiative corrections living in here. Where do they go? There's only one place for them to go, and that's in there. But this is the thing that you observe, essentially, the geometry. In sequestering, it's different. In sequestering, this guy is fixed by the ratio, because you've got these extra equations, the ratio of these fluxes. Okay, so this guy is fixed. This guy's allowed to move. So the radiative corrections from here, where do they go? Well, they go exactly where you want them to go. They go into here. And the thing that you actually observe, the geometry, remains fixed. So it's kind of, you're sort of releasing the straitjacket of GR in some sense. So here's a quick summary of what sequestering does before I move on to the work with Florian. But basically what's happening is this lambda, which is this counter term, bare cosmological constant, which you're now allowed to vary, it acts as a sink for the vacuum energy, and it gets pushed there by the fluxes. And this will work to any order in loops
what I presented won't deal with graviton loops, but there is a generalization involving the Gauss-Bonnet term that does. And you end up with a cosmological constant which is radiatively stable and which you should just go out and measure. Okay. So now I want to just switch direction a little bit, but I am going to come back to sequestering and talk about what Florian and I were thinking about. And it goes back to this story of self-tuning, self-adjustment. And so if you remember, we have Weinberg's no-go theorem, which says, you know, you hope for this, that you have radiative corrections to the vacuum energy, and they simply don't gravitate. Okay. Now somehow it looks like sequestering's getting around this. Okay. But there are lots of theories that don't. Okay. So what's going on? What is going on with Weinberg's theorem? Well, firstly we need to define what we mean by self-tuning or self-adjustment. So what we're going to say is that you emit a Minkowski solution regardless of the value of the vacuum energy. So for any value of vacuum energy, this is a very minimal requirement. Regardless of the value of the vacuum energy, you emit a Minkowski solution. This might not be phenomenologically viable, but this is essentially a minimal requirement for self-tuning. So Weinberg says, okay, fine, but he also makes some additional assumptions. He says that the theory should be a local 4D effective theory and that all fields are Poincare invariant. So for example, all scalars would be constant. Now, there are loads of examples in the literature of theories which evade Weinberg's theorem by relaxing various things, relaxing some of these assumptions. Okay, you can think of branes in 6 dimensions, Fab4 models, sequestering. Okay, some of these, many of these, run into difficulties in other places. Okay, as Ed will tell you, Fab4 died last Monday. But most of these other theories, they have problems. 6D models, for example, they can't recover 4D phenomenology. If you impose 4D phenomenology by compactifying the extra dimension, you spoil the self-tuning solution. Fab4 has this light scalar field which just kills you phenomenologically. Okay? And there's various other models have issues with ghosts, singularities, all sorts of problems. So Florian and I were thinking, is there anything that you can sort of, is there a no-go theorem here almost? Right? It smells like there is. Where you relax Weinberg's assumptions, but maybe bring in some phenomenology, phenomenological requirements to pin things down. So we wanted to be as general as possible. So we were looking at sort of field theoretic completions of self-tuning. So the idea was we take a standard KL spectral representation describing the exchange, the exchange of the amplitude exchange. Okay. So we assume that you could exchange via spin 0 or spin 2. Okay. We then impose unitarity and Lorentz invariance. It's very, very general. You can capture those 6D models, for example, very easily. We imposed unitarity, Lorentz invariance. We also required that at large distances you had some sort of self-tuning configuration, which you can describe quite easily. And then we also required that for short wavelength sources that you should be close to general relativity. And we asked, is this possible? The answer was no. It wasn't possible. You cannot fulfill all of these requirements. So it's telling you that there's no consistent field theoretic completion of self-tuning based on this. Okay, so people shouldn't get carried away with no-go theorems because they always wear a straitjacket. So we wanted to think of ways in which you could get around this. So one way you can get around this is you could generalize a little bit. So the result does generalize to asymptotically de Sitter space. It doesn't, however, generalize to anti-de Sitter space. So you can actually find explicit examples of field configurations in ADS space. So what do I mean by self-tuning in de Sitter or anti-de Sitter? What that means is that the value of the de Sitter curvature or the ADS curvature is completely independent of the vacuum energy. That would be the idea. So you can find consistent field theoretic configurations in ADS which
in which you have this notion of self-tuning for long wavelength sources, but on short wavelengths it just resembles GR. And then there's the sequestering loophole. Okay, now how does sequestering get around it? Well, the fields in sequestering, they don't have a standard, they're not built out of canonical free field propagators. Normally when you do the Cannon-Lehman spectral decomposition, you build it out of free field propagators. Okay, you can't do that with sequestering. You cannot build a sequestering theory out of field propagators. So it doesn't admit a standard KL spectral decomposition. What does it look like? It actually looks like something called decapitation. So this goes back to Ava Silverstein in the early noughties, and she was trying to address the problem of tadpoles. She had in mind, of course, hierarchy problem, cosmological constant problem, things like that, but also tadpoles in string theory. Normally, when you get a tadpole in your theory, you just add a counter term to cancel it off. Standard QFT. What Ava and friends suggested as an alternative was that you modify the propagator. So you introduce this decapitated propagator. The idea is that for non-zero momentum, it's just like a standard propagator. You're in Euclidean signature here now. For non-zero momentum, it's a standard propagator. For zero momentum, the propagator dies. It's zero. And this can be made completely compatible with unitarity, cutting rules, all that. So it's like what this does is this has the effect of literally cutting off the head of the tadpoles. It's like a guillotine. Now, what's any of this got to do with sequestering? Well, GR you normally think of as coming from an exchange of a single massless graviton. Okay? How can you think of sequestering? Well, locally it looks exactly like general relativity. So at least for non-zero momentum, it should just look like the exchange of a single massless graviton. But when you look at it more closely, what you realize, actually, locally you have a single massless graviton, you have a massless scalar, and you have a ghost scalar that effectively cancels off this unphysical guy here. Okay, so you end up with just the massless graviton propagating. However, at zero momentum, i.e. globally, it just so happens that this massless ghost gets decapitated. And so you're left with the massless graviton, but only at zero momentum, and the massless scalar. And actually what you end up with is the global limit of Fab 4, which is kind of cute. But this extra scalar, which is only allowed to do its work globally, because that's the only time when it doesn't get cancelled by this guy, is what readjusts to take care of the cosmological constant. Okay, so hang on. Oh yeah, so there was the Fab 4, just for Ed. Oh, the Fab 4's there.
Why is that not under the same pressure?
Oh, from neutron star mergers. Oh, because it's not the neutron star merger issue comes from the local part, right? It's to do with the local field. Here, the local theory is identically GR. Okay, so it's the results for neutron star mergers will be exactly the same as for general relativity. Okay, so well, let me just flash up the last few things, and then I'll just leave it open for discussion and questions. So I'll stop there.
Yeah.
Is there any way to test this theory? Does it have any prediction different from GR?
So that's a good question. Okay, so normally I would say I don't care, because at the end of the day, it has all the same predictions as general relativity. So
My question is it falsifiable?
Compared to GR?
In principle, is there any way to falsify this?
So, possibly. Even at the level of this, possibly. There's an interesting paper by John Turning and Shabasaki where they look at neutron stars and phase transitions within neutron stars and how the impact this can have on the mass ratio, a mass to size ratio of neutron stars. And what they have
so they consider two extremes. One in which there's no screening of the cosmological constants at all, one where it's complete. And they see that they get different prediction because you have phase transitions inside stars. This sees that or doesn't see it, depending on which scenario you're in. And it affects the ultimate mass to size ratio of neutron stars. Now, sequestering lies somewhere in between those two extreme scenarios. So potentially there could be some sort of signature there. See, this guy is This guy is sensitive to whether the local value of the vacuum energy though. So whether it's screened or not. Now, what happens when you have a phase transition in sequestering is, so what sequestering cancels is the borderline bottom lowest value of the cosmological constant, okay? But when you have a phase transition, you have a slight imperfect cancellation. And so sequestering is sensitive to that. So that's what I think you're zooming out. Having said that, we're now sort of trying to build this theory more into the UV. Now, clearly, from a quantum point of view, this is going to differ from the quantum corrections. This are ultimately going to differ from general relativity. Now, whether that's testable is another story. But we're also trying to build this theory more into the UV, trying to understand where these sort of global constraints come from in a more local setup. Now, there's some suggestion there that can be tied in with predictions for inflation that we can test, but that's ongoing work.
I have a question.
Yeah.
What quantum field theory calculation would I do to see that this really works? This mechanism really works? Because this is a classical.
Well, I mean, you could do the standard calculation for. Okay, let's just deal with the loops of matter. Okay, so you would do your standard calculation. You say I've got. I go to a locally Lorentzian frame. I calculate the vacuum energy corrections in Minkowski space essentially, because I'm in the local, and then I couple them back to the classical gravitational field in the standard way.
This is semi-classical.
Yes. So you could try to do a more general quantum gravity calculation in effective field, again with effective field theory. At the moment, what we're actually working on this. We're so with Sylvia Florian and Basim El-Manoufi in Sussex. We're doing it for the scalar version of sequester of this theory. So you can always, there's this, I don't know if you know about these sort of scalar gravity models where you basically just zoom in on dynamics of the conformal modes, and it has a lot in common with the full gravity theory. So we're working with that as a toy model at first, but the sequestering version of that, and asking essentially this question, doing it in a more self-consistent way. Once that's done and we understand all the pitfalls and all that, then, well, Basim has experience of doing this in full gravity theory, so we'll look to him to help us do it in the full case. Yeah. But always thinking of it as an effective field theory below the Planck scale, never pushing things above the Planck scale. Tassos?
So the free forms, can I see them as charges on the end of universe planes? Or actually, what is the boundary? Is it a timeline?
So at the moment we're not specifying what the boundary is.
Okay, but you have to live on a boundary.
Yes, well, you can think of them as indeed they. It's the sort of integral of the flux of the full form over the whole space-time, which you can think of then using Stokes' theory as the integral over the boundary. Yes, indeed.
So these three forms need to live on the same boundary. Could it be that you have a boundary on one side, a boundary on the other side? You have one form on one side.
So I think they have to be the boundary of our space-time as it stands. I'm not sure. I'm not sure about the answer to that actually. I don't know. Yeah, I don't know. Maybe not. I'm not sure. Pete, do you have a question?
How do trace anomalies behave in this question?
So trace anomalies. So
like truly quantum anomalies. How do they behave?
So I'm not sure about that. So I mean, I think okay. So I can think of this just purely in a. I can forget about gravity for a second, right? Okay. So when I forget about gravity, then everything is just standard. There's nothing. There's no surprises, because you should think of these lambda parameters as really being part of the gravitational sector. From the point of view of the matter sector, they're just a constant rescaling of the whole matter sector. So this doesn't do anything. It really doesn't do anything. It's just you've just rescaled. So effectively, we should think of is any mass scale in your theory, anything like, well, not that you'd have one in that case, but any mass scale in your theory is just being rescaled by a constant lambda, which is a meaningless statement, right? Until you start taking ratios against things that any ratio within the matter sector, those lambdas will cancel out. So I think purely from that point of view, you would get nothing new. Yes?
There is something not trivial about soft gravitons.
I think so, yes.
So I wonder if there's any connection with all that.
Me and Silver have been talking about that. Yeah, I agree. I'm very curious about that. I think it does smell. I mean, it could be a complete red herring, could have nothing to do with it. I'm not going to say this on camera, he's filming, so I don't want to say what I'm going to say. I'll tell you later.
What are the other natural problems you could tackle? This is a new way to tackle problems.
Yeah, well, hierarchy problem, right? Can you
actually tackle it?
So Basim and I I was in Sussex last week, had a very interesting chat on this. I'm more optimistic than I was. Yeah, in principle, I think potentially yes.
There was similar mechanism in.
Yeah, so the original obstacle to doing this was that we'd only formulated a question in a theory which had which neglected graviton loops. Okay. Now, when you're thinking about a hierarchy problem, now you can probably get away with that with gravity. You can just pretend you don't care about quantum gravity. Sorry, all the quantum gravity. But you could legitimately at least skip that question. With the hierarchy problem, you cannot ignore the issue of the Higgs loops, which would be the analog. Right. So this was how are you going to generalize that? That's troublesome. But now that we have this generalization as a question where it does take care of the graviton loops, it does make it more promising to sort of think about the hierarchy problem. And so we're kind of, maybe. So that would be the idea. And again, this scalar gravity is actually a nice playground to think about that, because you're now really dealing with scalars and things like that.